Tel Aviv University. The webinar is based on an opinion article I recently wrote for the Autonomous Vehicle Technology magazine. Feel free to look it up on Innoviz social media channels. The session is recorded and will be sent to you in the days after the webinar. The webinar will discuss the following topics: the sensing technologies used in autonomous driving, namely camera, radar, and LiDAR. We will explore the strengths and weaknesses of these technologies and also analyze the synergies between them. We shall also discuss sensor fusion as it is related to the sensing technologies. However, it is not the primary goal of this webinar. Then we will try to answer your questions in a Q&A session. To make logistics simpler, the audience is muted. However, you are invited to submit your questions using the chat feature. Finally, we will conclude the webinar with a short summary. When we talk about autonomous driving, we actually mean that the driver waives the driving functionality to a machine. In other words, the driver loses control of this task. And we all know that losing control is not something people like. A poll conducted by Survey USA on 1,200 American adults last March found correlation between the knowledge of respondents in autonomous driving technologies and between their confidence in these technologies. So perhaps trivial, but very simply put, the more we know and understand a technology, the more we trust it. And it is more prominent with autonomous technologies in which people waive control and hand it to a machine. Bottom line, if we want consumers to adopt autonomous driving, the knowledge, experience, and trust must be obtained. So the question is, how can we further increase trust? What should we do? At Innoviz, we believe that ensuring customer safety should be the key design goal of autonomous driving, and therefore, we're hosting such webinars to help and shed some light on sensing technologies. Let's understand why these sensing technologies are required. The best analogy to autonomous driving sensors are the human senses. So why do we, humans, need multiple senses to comprehend our environment? Setting aside the biology aspects, let's consider the following. Objects have varying signature stamps, such as sound, size, smell, color. The more ways we comprehend an object, the better classification we have. And with improved classification, we have certainty. Is it a friend or a foe? The classical fight or flight dilemma. Finally, we need to think safety. What happens when one of our senses fail? For example, vision impaired or hearing impaired have many capabilities as they have other senses to use. Similarly, what happens when a camera or radar fail? What replaces them? Bottom line, multiple sensors increase certainty and redundancy, which leads to a much greater confidence in the overall performance and safety of the system. Let's talk about the technologies. When referring to autonomous driving sensors, the prominent technologies are camera, radar, and LiDAR. Ultrasonic is another sensing technology used in vehicles, but it will not be discussed as its functionality is fundamentally different than other sensing technologies we are discussing today. Each technology is further subdivided by functionality or specification. For example, there are long-range, mid-range, and short-range radars, each having a different functionality and specifications. Today, we will focus on the variants that are the closest in their functionality to the LiDAR, which are the forward-looking camera and long-range radar. Let's start with radar, which stands for radio detection and ranging. Radar goes back to the late 19th century, but was mainly adopted with the introduction of air defense surveillance systems in World War II. Radar operates in the microwave part of the electromagnetic spectrum. It sends out electromagnetic waves, hence called active sensing, which are reflected from targets and detected by the radar system. The system provides distance and direction to a target, hence three-dimensional, as well as direct measurement of its dynamic parameters, such as velocity, through Doppler shift measurements. The technology is especially good in harsh environments, such as low light, bad weather, and extreme temperatures. First automotive radar was introduced by Daimler, back then Mercedes-Benz, in 1998 for automatic cruise control. Today, radars are used in multiple applications and are subdivided mainly through detection range. They are considered to be a mature and relatively cheap technology, taking into account many generations since first introduced. Switching to camera, which operates in the visible part of the electromagnetic spectrum. It detects electromagnetic waves which are reflected from targets by the sun's light, hence called passive sensing. Cameras usually provide direction and classification of targets, as it is especially good in semantic and color recognition. But cameras have two fundamental flaws. As they depend on external light, cameras are very vulnerable to harsh environments or completely non-functional, such as low light and bad weather. Regular cameras also lack the ability to provide range, as the basic technology is only two-dimensional. Toyota introduced an automotive camera in 1991, and it was used while reverse driving the vehicle. In 2007, Mobileye launched multiple systems for serious production for lane departure warning on General Motors and BMW vehicles, and also radar camera fusion for adaptive cruise control on Volvo vehicles. Today, cameras are used in multiple applications and have many different variants, such as front-looking, surround, and near-infrared cameras. Cameras are considered to be the leading technology in ADAS due to its low price and perception capabilities which are similar to human perception. One word, near-infrared, short-wave infrared, or long-wave infrared cameras. They definitely have the potential to be integrated as additional technologies in autonomous driving, but this is dependent on their maturity, the ability to mass produce the technology, and its price. Time to market is especially important in trying to predict if such technologies will be added or not. Finally, LiDAR, which stands for Light Detection and Ranging. It was first introduced in the automotive industry as part of the DARPA Grand Challenge in 2004 with LiDARs from Regal and SICK. In 2005, Velodyne introduced its first LiDAR, the HDL64E, in the second DARPA Grand Challenge. Since then, LiDARs have been used in most development fleets of autonomous vehicles. LiDAR operates in the near-infrared part of the electromagnetic spectrum. Similar to radar, it sends out pulses or continuous electromagnetic waves, hence active sensing, which are reflected from targets and detected by the LiDAR's detectors. It is especially good in low light conditions and relatively good in bad weather. The system provides distance and direction to a target, hence three-dimensional, at a very high resolution and a long range, therefore making it the perfect sensor to find all those small obstacles on the road that are potentially risking the vehicle and its passengers. The picture in this slide shows an incredibly detailed image of the Innoviz parking lot created by a single Innoviz one frame. LiDAR is the youngest of the three technologies, hence the least mature, which is reflected by a higher unit price. But significant price reductions in the past years, especially those introduced with solid-state LiDARs, made it possible for vehicle manufacturers to integrate LiDARs as an important sensing technology in their autonomous driving projects. The first and currently the only generation of automotive LiDAR was introduced by Audi in its A8 at the end of 2017 using Scala by Valeo. So we understand what LiDAR is, but why has it become such a prominent technology in the last 3 to 4 years? Until 2016, LiDARs were mechanical. Systems were simple in design, usually coupling a laser with a detector, multiplying this in the vertical axis and spinning the entire mechanism horizontally in 360 degrees. But the technology had performance limitations, incredibly high unit price, difficulties in scaling up the performance, and a very large and bulky size, making it impossible to integrate with mass production vehicles. In 2016, Innoviz was founded, introducing an automotive solid-state LiDAR, solving all the above issues of performance, price, size, and durability. So the opportunity to car manufacturers of adding a LiDAR in their mass production autonomous driving projects became real. As LiDAR is not as known as cameras and radars, let's have a few words on this technology. LiDARs are usually classified by three attributes: the wavelength they use, the way field of view is created, also known as beam steering, and the method they calculate the range to a target. As for the wavelength, Innoviz chose to base its technology on the 905 nanometer wavelength, range, as it is a mature and cheap technology. Devices are silicon-based, which makes their fabrication mature, efficient, and simple. There are other wavelengths used in the industry, as can be seen in the slide. As for beam steering, there are a few major technologies which are used in the industry, but there are many sub-variants. Hence, it is probably the area in which LiDARs are mostly different one from the other. It is also the area in which most LiDAR companies innovate and differentiate their technology. Innoviz chose a MEMS-based design beam steering. Similar to the wavelength considerations, we understood that price, functionality, and maturity are critical for automotive mass production. Hence, we relied on the maturity and pricing of the MEMS technology. Innoviz has developed its own MEMS mirrors, and these provide the unprecedented performance. Finally, distance measurement. LiDARs are divided to those emitting laser pulses and those which use continuous waves. Here as well, Innoviz chose to use a simpler and a cheaper mechanism of measuring time of flight pulses. This means that the system calculates the time from which a laser pulse was emitted to the time photons which were reflected from the target were detected. Okay, so far we introduced the sensing technologies. Before we discuss their differences, let's shortly discuss the sensing needs of autonomous driving. So the basic question is, what do autonomous vehicles require in order to drive safely? Naturally, the basic need is comprehending the road ahead and its uses. Easy said, but very difficult to achieve. The sensors need to detect all possible obstacles from small, like tire debris, to very big, like an overturned truck. All possible road users, such as pedestrians, vehicles, motorcycles, and trucks, must not only be detected, but more importantly, be recognized. Why? Take an example, a motorcycle which behaves completely different than a truck. This is crucial for predicting the driving scenario. And driving infrastructure, such as road signs, traffic lights, tunnels, guardrails, are important for the driving maneuvers, as well as driving path planning. Also, the vehicle must comprehend its own driving, also known as ego motion, and path planning with respect to other road users. For example, an autonomous vehicle cannot change lanes if it is not 100% certain that it does not cut other vehicles by doing so. The next obvious need is availability. Sensors cannot operate just part of the time or have very limited functionality. Safe driving requires fully functional sensors, and so sensors must be usable in all driving use cases such as highway, including both fast driving and traffic jam situations, urban driving, etc. Also, as driving scenarios are never similar, sensors need to cope with new and unfamiliar situations. Availability also requires possible 24/7 operation, which means all lighting and weather conditions. Finally, sensors need to provide the autonomous vehicle with the confidence to decide. Of course, 100% confidence in reality is impossible. There are always mistakes. But sensors are still required to evaluate themselves and estimate whether they are working properly or not. Also, they need to attach a confidence value to each estimated parameter they output, meaning how certain is the system with that parameter value. We're now ready to move to the next chapter discussing the technical differences between the three sensing technologies, and I'm passing the mic to Professor Giryes.
Okay. So what we'll do now is that we will survey the properties So what we'll do now is that we'll survey the properties of the different sensing technologies that were mentioned. In particular, we'll talk about compare radar, camera, and LiDAR. So in this scheme, you can see an overview of the comparison between all. And you can see that each device has a different advantage compared to the other. And this scheme emphasizes the main advantages of each device and show that all of them are essential for making autonomous driving. We will focus on some of these properties next. And for example, you can see in this scheme that LiDAR has a major advantage in small object detection and low light performance, which are of immense importance for autonomous driving. Okay, now we start with a technical table that show that the main technical properties of each system. So for example, you can see here that camera provides us with 2D color information, while LiDAR gives high resolution 3D information with reflectivity that is absent from the 2D information of the camera. If we look at a high resolution radar, so it gives us low 3D resolution and a velocity estimation. Another thing that LiDAR gives us compared to the other devices is that it is of very high resolution, which make it more resilient to spoofing and phantom objects. Now we'll turn to focus on some specific properties, and we will start with the spatial separation. For spatial separation, we have the following diagram that shows us that the resolution of a measurement system depends on the wavelength used and the collector size. So here you can see the wavelength of a LiDAR and the camera and the wavelength of radar. Now, using the formula that relates resolution to the wavelength and the collector size, we can see that in the case of LiDAR, the wavelength is 1 micrometer, which is similar to the one of a camera. And therefore, both of them achieve a similar angular resolution of 0.1 degrees. On the other hand, if you consider the case of a high resolution radar, the wavelength in this case is much larger, and therefore the angular resolution is much worse. The same holds for the depth resolution. LiDAR achieves resolution of 1 millimeter, which is 2 orders of magnitude better than what you get with radar or with high resolution radar, which is 15 centimeter resolution. And notice that with radar, you need also much larger collector. So this shows that if you want accuracy, you get with LiDAR things that you cannot get with radar, and you can get also depth information. We now consider the semantic perception of each system. So if we compare a camera to a LiDAR, where both of them in some sense give us high resolution information, camera focus on the color of the scene that it's looking at or it's capturing, and LiDAR give us the depth information. Now, in some scenarios, looking only at the color will make us miss some of the objects. So see this example. With LiDAR, we can see objects marked in the right image that we cannot see in the left image because of the color ambiguity. So you can see the small objects in the right image that you cannot see on the left. And another thing is that when you look at the RGB image of the camera, it is very hard to distinguish between the road and the border, which is easily distinguishable when you look at the 3D map of the LiDAR. So getting this information is very important for estimating drivable areas where semantic classification of entities and ground is a critical element. So here you can see an example where using just color or just depth let you miss some object, and this shows you that you need both of them. Now, one may inquire whether we could have achieved the same result that we have shown in the previous slide also with radar. Now, for that, let us consider the problem of small object detection. So, as we have mentioned earlier, when we looked at the wavelengths, Radar measures velocity of objects, and you can see it on the right image that gives us a demonstration of that. And it depends on the Doppler effect, but the way it measures things lead to a poor spatial resolution of the 3D world. So you can see here the 3D map of a high resolution radar and the 3D map of a LiDAR, and you can see that with LiDAR you can distinguish between an object, you can understand the world better, and you can detect small obstacles, which you cannot do with radar because you will miss lots of information. Another very important case when you drive is low light conditions or driving at night. In this case, the camera performance degrades significantly, and it can miss many objects. LiDAR, on the other hand, excels at low light conditions. In the example that you see in this slide, observe how the two pedestrians in the camera are invisible while they can be clearly seen in the LiDAR. Now, notice that an ideal environmental setting for one sensor, LiDAR in this case, which excel at low light conditions, could be the worst for the other, which is the condition for camera. So it's very hard to see with the camera at night. Therefore, using a fusion of different sensors is essential to make autonomous driving safe. Another important aspect is resilience to weather conditions. Now, in this case, radar achieves the best performance. Yet, as we have shown before, it cannot be used for object detection because of its poor resolution, and therefore we will focus on comparison between a camera and LiDAR, and we will show the case of driving when it is raining. Now, here you can see example of image captured with the camera in the case of rain, and the same scenario with the LiDAR. Now, because of the shutter speed of the LiDAR and its scanning strategy, it is less sensitive to rain compared to the camera. You can see here how the raindrop, together with the sunlight, strongly affects the visibility in the camera. In the top image, we cannot see the car that is clearly visible in the LiDAR on the right. In the bottom image, the bus and car are distorted, which might be visible to a human eye, but will almost surely fail with any machine learning-based algorithm that is commonly used today with autonomous driving. In the LiDAR scan, the object looks the same with the rain, without the rain, and therefore you can use the same machinery that is used in clear weather conditions, which is very important. Another important factor in safe driving is being robust to changes in the capturing conditions. Now, here you can see the case of the recent Tesla accident, which can demonstrate how important it is. In this accident, a car crashed into a truck lying on the road. The truck was not detected by the camera because of the reflectivity of the covering of the truck, and the camera detected the truck as part of the road, and it seems that the radar failed as well because of the scattering of the covering of the truck. So on the right, you can see the front view of the camera, and on the left, you can see another way, the same accident from another angle. Now, the next slide, we'll see a short video prepared by our partners from Cognata that simulate the scenario seconds before the Tesla vehicle hit the overturned truck. Now, in this simulation, we simulated the same scenario with LiDAR, and the LiDAR clearly showed that if you would use a LiDAR, we would have prevented the accident in this case. So you can see here the top view of the driving car and the object on the road. In a minute, we will see the frontal view. And our partners from Cognata simulated the expected Innoviz 1 point cloud based on the specific capabilities of the system. And notice that the reflectivity and scattering of the static object that confuse the camera and LiDAR do not affect the LiDAR scan that clearly observe the big lying object on the road. So if you'll see again the movie, you can see that in the LiDAR, we clearly see the truck that before was not detected by the camera and by the LiDAR. Now, if here also we applied our machine learning techniques that detected that the car is a non-driving object, and you can see in green that the road on which we can easily drive. So these examples show us how important it is to use all three sensors together and not just a single sensor. Another important case is a sudden change in the lighting condition, as is the case when we enter a tunnel. Before we enter into the tunnel, you can see here that the camera clearly detects objects outside the tunnel, but not the cars that are inside the tunnel, which are observed by the LiDAR, as you can see on the right. When we enter the tunnel, the car and truck are much less noticeable by the camera, while the LiDAR sees both and another car that is in front of them, as you can see on the right. When we are inside the tunnel, it takes time to open the shutter or increase the exposure, which makes the truck invisible to the camera while nothing changes for the LiDAR. So here, this is another example that shows why we need more than one sensor. Another prominent example of an unexpected change in the light condition is a sudden direct sunlight that appears. On the left, you can see that the sun is covered by the bridge, while half a second after, it appears and dazzles the camera, and therefore nothing can be seen. And this will not happen with the LiDAR. Another artifact is that when you use color information, is color confusion. On the left, the yellow lane marking is distinct from the barrier. Then the camera merges the yellow barrier with the lane. And then you can see that the car here on the front hits the barrier because it confuses the barrier with the yellow lane. And again, if we would have the depth information, this accident would be prevented. So if we summarize, each of the sensors has its unique advantages that make it essential if you want to have a safer driving. Now, and this clearly answered the question, which sensor should we use? And the answer is we should use all of them. And for this, we should fuse all sensors together. So there are several factors that make this answer so clear. First, when we take into account the cost versus performance, we have seen that the benefit of more sensor, which costs more, outweigh the cost. There are clear cases that if we will remove one, will lead to a clear failure, which can be easily prevented if we would use all the sensors. Now, indeed, sensor fusion is a challenge by itself, and one needs to decide what information should be included from each sensor. Yet it allows to cope in a good way with failure and recovery, which are cases where one sensor fails, and then the other can be used to keep the car moving safely.
Okay, so moving to questions, and I would like to remind you that you're able to submit questions via the chat feature. So we'll start with two questions that we are often get asked. The first one is what we call the Elon Musk question, which has repeatedly, Elon Musk has repeatedly stated that LiDARs are not required for autonomous driving, and how do we answer such a claim? We definitely hope that this webinar was answering this question, but if not, let's go back a little bit and describe what we discussed and a few more topics. So a need for a LiDAR is not only performance or the capabilities of the system. It has other aspects, as we discussed, such functional safety, regulation, consumer trust, etc. Say that we want to analyze just the performance for a second, then going back to Elon Musk, we need to remember that Mr. Musk is a CEO of a public company selling a specific product. So he's taking a side and a stand of justifying Tesla's specific solution. It is not an objective stand. And by the way, so Innoviz is not having an objective side on this matter. So we would like to switch to somewhere else on Waymo in a second. But just bearing in mind that changing the statement of Mr. Musk, that assuming that he says that now LiDAR is necessary, it has a profound economical cost on Tesla, as customers bought their autonomous driving feature for more than $7,000 US dollars based on the assumption that the hardware is there, and it's only a matter of a software version. Furthermore, as we've seen in this webinar, Tesla's accidents are not a coincidence. It's a matter of system design. So now let's talk about Waymo for a second. So Waymo is probably the most experienced company other than Tesla in driving and developing autonomous driving platform. And they heavily depend on and use LiDAR technology. So much to the extent that they have decided to develop their own LiDAR solutions. They claim that LiDARs are necessary in autonomous driving, and we can only believe that such capable engineers would have waived LiDARs or decide not to use it and save money if they have thought they could develop an autonomous driving platform without a LiDAR technology. So I hope this answers the Elon Musk question. Oh, okay.
Another question is, will thermal cameras will replace LiDARs? So as we discussed, thermal cameras definitely have the potential to be integrated as additional technologies in autonomous driving, but this is dependent on their maturity, the ability to mass produce the technology, and the price. The time to market is especially important in trying to predict if such technologies will be added or not. And we believe that due to the maturity and the project timeline, LiDARs will be added to the autonomous driving projects before thermal cameras. Now, this means that adding thermal cameras in the future will be dependent whether they add the missing functionality or if they can completely replace an existing technology with improved performance and pricing. Now, this is a major challenge that companies developing thermal cameras need to prove. Another important aspect with thermal cameras is that as regular RGB cameras, thermal cameras do not give us depth information, and reflectivity, which are given by LiDARs. So the absence of depth information is something that is crucial, and as we have seen previously, depth information is very important for understanding the scene, and we cannot get these things with thermal cameras, and therefore I don't believe that they can replace LiDARs.
Okay, a few more questions that we get now using the chat feature. So first of all, yes, the presentation will be shared. As we initially said, it will be sent out in a few days. There's a question on which of the three technologies is best for augmented reality glasses. This is a little bit out of scope of our webinar, so I'm sorry, but our expertise is in automotive industry and technologies, and less on augmented reality glasses. So I'm sorry for not answering on that. There was a question on night vision camera, thermal and gated imaging, and we believe that this was answered just recently by Professor Giryes. There's also a question on how light signals that enters the receiver are being processed. Yeah. So yeah. Okay.
Okay. So I assume that the question about how light signals that enter the receiver are being processed refers to the LiDAR technology. So LiDAR technology is time of flight technology that emits laser light and then measure how much time it takes for the light to go and come back. Each LiDAR has a different way to process things. The solid state LiDARs as used in Innoviz, so we have some array of mirrors that know where to direct each light ray, and then measure the number of photons that returned and how much time it took them to return. And this allows to make efficient processing of multiple rays and get in an efficient way the depth of the scene. Now, another question is what is Innoviz depth measurement accuracy? So today, the measurement accuracy that Innoviz get for very large distances is 1 centimeter, which is what is required for autonomous driving.
Another question is on our view of the LiDAR concepts where a camera helps the LiDAR scan a region of interest. So basically, this is a fusion on the level of sensors. This is something that we believe it is not, well, at least the path that Innoviz chose is to provide the LiDAR by itself and not to fuse it with other sensors. We believe that eventually the sensor fusion should take the basic information coming out of each technology. Once you use, for example, a camera for LiDAR or vice versa, then you kind of contaminate that basic technology with another technology, which means that the overall sensor fusion is not independent. And therefore, we believe that the sensor fusion should have independent sensing technologies and not intervened. There is also a question about LiDAR performance in heavy rain, mist, or snow. As we discussed earlier, LiDAR is better than cameras in bad weather. Not as good as radar, though. Of course, the performance is highly dependent on many attributes, also on the lighting condition in general. So for example, if it's a heavy rain in night, it will be better than if it's a day. Also on the reflectivity of the target and other parameters. But in general, the Innoviz LiDAR, we've already proven that it's possible to function under bad weather conditions as well. So another question, is it possible to have a surround view LiDAR system with Innoviz sensor? Excellent question on whether it's possible to have a 360-degree LiDAR. We would probably think that a solid state having 360-degree would be kind of a holy grail for many, many applications. And that's as far as we can comment on that. Okay, so far for questions. Oh, sorry, which frequency you use? Yeah, so we've discussed that Innoviz uses 905 nanometer. It's the lower part of the near infrared spectrum. How long does it take to have a confidence object on the vehicle interface? Okay, so in general, on the information of object detection, there are a few latencies associated. So the first one is how fast we can provide point cloud to the vehicle, and that's fairly quick. The latency is in few microseconds. Then there is a layer of object detection. That, of course, is depending on the frame rate and other parameters that we measure. But overall, it would be a matter of between 2 to 3 or 4 frames until we get all information. But usually the basic information is provided in 2 frames. Okay, I think these were the questions. Oh, there are popping up some more. What do you think? When can be the first introduction of FMCW LiDAR on automotive market? And does Innoviz planning to more into this direction? So I'll start with the second one. Innoviz, as we discussed, or let's go back, FMCW is always associated or has to use 1550 nanometer wavelength range. Currently, although it has some advantages, we do not believe that is a technology we want to pursue. We chose Nano 5, as I stated earlier, because of its price and maturity and because it's a silicon-based technology. 1550 uses what are called 3-5 materials. It's in a very expensive fabrication process and relatively immature in this industry. Maybe in the future, but currently this is not the direction we're pursuing. If it would be introduced, at 1550 or FMCW in general, it's a more expensive technology. Whether it could be produced in viable costs and prices to the automotive industry is a very, I would say, difficult question at this point. Okay, I'm sorry, we have more questions, but we do need to wrap up. So I'm continuing and making a summary. I'm sorry. Yeah. Okay, so I'm getting the signals to answer one more question. So we have, how does your technology compete with Waymo's? With Waymo's LiDAR? So the LiDAR that Waymo, I would say, make public and to sell to the general market, the Honeycomb was a little bit different than what we have. They also seem to have their front-looking LiDAR or the long-range LiDAR. And here we don't have their specifications, so it's a little bit difficult to say how good are we or not. Okay. Moving to summary. I hope that we answered most of your questions, and I'm sure that we will go back following this webinar and verify that we answered everything. And if not, I guarantee that we'll send each one of you the answers and our comments to the questions. And I'm sorry that we had no time to go for every question. So let's have a short recap of what we have discussed today. So the core theme of this webinar was addressing a question which is raised once in a while in the automotive industry, whether a LiDAR is really needed for autonomous driving. We believe the answer is fundamental yes, and there are many reasons for that. First, performance and availability. Simply put, camera and radar alone cannot cover the entire range of driving use cases, let alone do it safely. Second, functional safety. We're familiar today with ADAS. In ADAS, the driver is in full control, both legally and operationally. But we're transitioning to autonomous driving, in which there is no driver intervention with critical decision-making procedures, such as automatic emergency braking, cut-in scenario, etc. This is a major difference. In autonomous driving, the system cannot have a momentary lapse of reason. It must operate at all times and at all conditions. And because failures do occur, immediate backup is mandatory to come to a safe state. Third, we discussed the importance of public trust. Consumers will accept autonomous driving technology if they understand it, but also if they trust that the technology is safe. And since 100% is always not guaranteed, consumers would want to believe that the automaker did whatever it could in order to maximize safety. Considerations such as unit price are less accepted when it comes to human lives. Last but not least, regulation. Regulators have hard times keeping up with the technology. We all want regulation to support technology instead of limiting it. But we also want regulation to be a safety net and protect from wrong usage or cutting corners. When regulators authorize new technologies, they always prefer to walk on the safe side. Therefore, adding capabilities and safety can only expedite regulation of autonomous driving. So that's it for today. Thank you, Professor Giryes, for joining me. We hope that you found this webinar useful in tutoring. We look forward to getting your responses and comments, and we promise to answer each of your questions. And I would like to remind you that the session was recorded and will be sent to you in the coming days. Thank you and goodbye.